can't drag the hand. That'll work.
How do I drag this thing? Oh, there we go. That's right.
Now, before you go any further there, Ben, what's going to be the difference if it says you don't have a square base? You just have another variable. Does this one have a top or not?
No, it's not.
No top. Okay, so we're not going to have the same. Why don't you label on the box there your variables so we can see what we're doing? So I'm going to build a 3D diagram of the cube there.
Oh, okay.
Label what your variables are.
There you go. So say, okay, so just a square base. So this can be anything.
Right, we don't know what that is.
All right.
It's got to be an H.
So this is going to be W. Then all these are going to be H.
Correct. All the insides.
Gotcha.
So when you have that surface area equal 5W squared, you want to change that?
Yeah. Okay.
Where did your 5W squared come from?
5W squared.
I think you were interpreting that as
Oh.
if the height was W.
Yeah.
You want to change that.
Yeah, I want to change that. So. So I guess just this one is going to be W squared, right? The one in the middle. Okay. So now we just solve for H, right?
Correct.
Okay.
And then it said we want volume in terms of height, solve for W.
Yeah.
It said it defines volume in terms of width. There you go.
Can we simplify that possibly?
Mm-hmm. Yeah,
Okay.
this should be. Don't distribute it that way. Take the W squared and the 4W squared is on the outside of the parentheses, not on the inside.
Oh. Oh, yeah, okay. That's what that.
Close. You still have the 2 next to the W.
Well, we have two separate fractions.
Right. So you have either 1/2 W minus W cubed over 4, or you can.
Right, this first one.
Yeah. Minus W cubed over 4. Expanded. Good. So everything is in terms of W, no more H out there.
Yeah.
Questions on that guy right there? Yes, ma'am.
Where is he getting W squared?
Where are we getting W squared plus 4WX? Okay. We have a box with no lid. And the base of the box is a square, so W times W, W squared. The length width of the 4 sides is WH, and there are 4 of them. That's where that is coming from. Yep. So here, let's look at this panel of the box. Let's pull that panel out. Here's what it looks like.
Okay.
And there are 4 of them.
Oh,
So we got 4 WHs. Yes?
yeah.
So I add that to the base, so the W squared plus 4 WHs. And I get my surface area. But it told us the surface area was 2, so we just set that equal to that equation above, and now we take that and solve it for my height.
Like, I don't understand where you're getting, like, I don't make sense.
You want to come up and show?
It says volume of the box is a function of the base width.
Right.
How do you know what that looks like?
Okay, so when it says I want to find volume as a function of the width of the base, we're talking about everything needs to be in terms of, because we use the variable W, I'm going to have to say V of W. Had I used a different variable, X, whatever, I would have V of whatever that variable is. So if the volume of this box, generically, the volume of this box is W squared, right, length times width, and then now times height. That's the generic formula for the volume of this box. When it says I want everything in terms of a W, I have to change this H of that formula into something that just has W. And that's where all of this work came in. So we had a surface area that has W and H. We used that to solve for H, and now H is just in terms of W. So we're all based on the same value now. We're all based on this width number, whatever it is, of this box. So now everything is a W. You plug that back into my volume equation and simplify. These problems can always go 2 ways. You can express volume as a function of the base. You can express volume as a function of the height. So I can go either way. But I'm always going to have another equation that I can use to rewrite for whatever this variable is that I'm supposed to change. Does that help, Caleb? Are you sure? Sort of. All right. Any other questions on this one before we go to the next one?
okay if we write the answer as 2w minus w equal 4? Or just have to be
Yes. Yeah, so you could have canceled. So right here, I could have done this. I could have factored out a w squared, well, even a w squared, doesn't matter, and had a 2 minus a w squared all over 4w. And then, yes, you could have canceled one of those w's with this, and had that as well.
Okay. Thanks.
All right. Here's the one that's going to get you. All right. Now again, if you don't have a sketch, it's going to be hard to do these things. So we want to make sure we're drawing these correctly. So let's make sure we understand the concept. We've got a path running north and south. That's intersecting with a river running east and west. And at this intersection point O, we got a rider on a horse. And then we got a boat. And the rider on the horse is going to start from that point O, and he's going to, or she's going to travel north at that speed, 12 kilometers per hour. At the same time, the clock ticks. There is a boat that is 25 kilometers to the east of O, and it is proceeding to travel in a westerly direction, which means it's traveling towards O at 16 kilometers per hour. And we want to express the distance between this horse and this boat as a function of time. All right. So here is our sketch. Again, if you don't get the sketch, it's going to be hard to get the problem. So we have our rider. So first of all, point O. We have our rider. Remember we talked about vectors yesterday. Vector is an arrowhead and a tail and head. The length of the arrow can represent the magnitude, or in this case, the distance that we're traveling. And the direction of the arrow would determine north-south. So we have that as our horse, and that rider is going 12 kilometers per hour, and again, that is a rate. That's an R. At the same time, we start the clock way over here, which, by the way, is 25 kilometers away, to the east. We have this boat. And this boat is going to travel towards point O. And it travels at a rate of 16 kilometers per hour. And at some time t, those two will be some distance away from each other. So here is the triangle. This is the essential part of the problem, right there. That's the triangle we're looking at. Notice where I created the triangle. It goes from the head of the boat vector, not the tail. Because I've already traveled this much of a distance in however long it took us to do this. We don't know. But I've already traveled that distance. And so this line here, this dashed red line, represents how far this rider and the boat are away from each other. So highlighting a place where people get stuck on this is they will draw their triangle here. And that is a no-no. Do not draw a triangle. Going from head of a vector to a head of a vector. All right. Okay, so there we are. We got our right triangle. And we are looking for the distance between the horse and the rider as a function of time. That means we're looking for this. Which means we need the blue. We need to know how long this length is from O to where this boat is currently. So when we were doing this stuff yesterday, we said we want all our triangle parts to be the same. And we want them, in this case, to all be at distance. And we're not quite there yet. Yes?
Wouldn't you want them all to be the red if you want the distance between the horse and the boat, not the stuff on the boat?
Say that again?
Is it distance t between the horse and the boat? Wouldn't you want the hypotenuse because you're going from where the horse is at t and where the boat's at t? Because the horse...
I'm wanting this distance right here.
Correct.
Yes. Oh, what did you say? No, we need to know the blue. We need to know this distance so that I can set up my distance formula for the triangle. You're right, I am looking for the red, but I need to know this distance of the blue so that I can find the red.
Gotcha.
That's true. So, again, we're expressing distance as a function of time, and we know distance is equal to a rate times a time. And so we have, with each of these kilometer per hour, if I just simply multiplied by t, I would have now a distance for each of those. 12t, 16t, now I've got a distance. It's distance as a function of another variable. So I've got everything that I need in the way of distance, with the exception of this. We need to find that. So if I want to find leftovers or something, how do I find leftovers? Yeah, we subtract. So this question mark would be a distance of 25, good job, minus 16. That's what this is. Okay, so let's say we're going from Roseville to Auburn. Roseville to Auburn is about 16 miles. And I have a buddy that leaves Auburn, and they're coming back to Roseville, and they go 2 miles towards Roseville. How far are we away from each other? 14. How do we do that? We just subtracted, right? We just took the total distance and we removed what we knew. That's the same thing that happened here with the blue. At 25 kilometers where the boat started, the boat has already traveled a distance of 16t. They've already traveled that distance, which means the leftovers have to be 25 minus 16. Is that up?
Why multiply both for distance?
Because we need to express distance, and distance is a rate times a time. Good question. All right, before we go any further, are there any other questions with where this 25 minus 16t thing came from? So then we're ready to see distance formula or Pythagoreans come into play here with our right triangle. 12t squared plus 25 minus 16t quantity squared would equal d of t squared. This is how we're going to find our solutions. So we're just setting up distance formula. 12t squared t squared. And then, let's work here. 144t squared plus 625 minus 400. Yeah, no. Yeah, 400. So 625 minus 800 t plus 256 t squared. And all of this is still underneath the radical. All right. Combining the 400t squares minus 800 t's and then plus 625. I'm okay with leaving our answer this way. However, you can simplify this. like you can pull out at least a 25 from each of those. And then you have a 5 that's hanging out in front, right? You have a 5 times the root of whatever the leftovers are. But that's our distance formula as an expression of time only. And then from this, if we wanted to, we could answer those questions like, when will they be closest to one another? So again, here's that quadratic under our radical. We can set up our axis of symmetry, find that time, and then we can plug that value in to find out actually how close they are to each other at that time. So there's a couple different things we can do from this problem. Another tweak that I could place on a problem like this is have the boat go the other way. Now what do we do? How does it change the problem if the boat goes the other way? Yeah, so now we're taking the 25 that the boat started at, and we're going to add to it the distance that it has traveled. Okay? So that's why the important thing is the sketch. Another mistake that somebody will make drawing this thing is they'll assume that everything is started at point O. So you have to read it carefully. You didn't start the boat at point O. You started the boat a distance away from point O, and then you're coming to it. So there's all kinds of tweaks you can do. But you'll notice they all set up as right triangle problems. Once we get to chapter 7, where we start talking about non-right triangle problems, we'll be using law of sine markers. What questions do you have for this one? Once you get it set up, it's good. It's the hardest part again, always get these things set up. We all right? I'm going to let you guys try and tag team this with each other. I'll help you with the rate part of the problem, but I want to see if you guys can come up with the solution. I will also give you a hint that similarity comes into play with this problem. So let's get the picture. Got a cone. That cone, water is being put into the cone at a certain rate. So I've got 40 cubic centimeters flowing into that cone per second. And I know the dimensions of the cone. So I've got this 100 centimeters wide. 250 centimeters deep. Okay, so we're not quite the proportion. And by the way, if I ever have sketches on a fun times, don't assume they're proportional. What else do we know? We got water coming in. We got water flowing in here at 40 cubic centimeters per second. What is that? It is a rate. So this is a rate. That's going to come into play when we write our problem. Which means I can express volume is equal to a rate times a time. There's part of the trick to the problem right there. And then find the volume of the tank as a function of the height of the water. So water's coming in here, and at some point in time, the water's there. And then as it keeps filling up, obviously the water level changes. So we've got this generic, we'll express this as height of the water for our H. But we know that the tank is, well, we already know that the tank is 250 centimeters. All right. So let's see if we can get this one out here. Height as a function of time. We've got a couple different things. We've got volumes of a cone. We've got rates going into the cone. Again, hint on similarity figures. We've got similar figures here. So why don't you guys partner up with somebody, see if we can come up with a solution for this one. So here's the big, to the edge of the full cone. What's this distance right here? Good job. It's half of my diameter. What is this distance right here? 250. there's our cone. Half of it, full cone, assuming we fill the whole thing. Now we go look at just what happens with h centimeters of water in the cone. So I have this. What's this happening? Well, generically, what would this be? It's just a radius. That's just a radius. And then I could take these two and set up some proportions and see what we get. Could you express the height as 250 minus? Well, that would, if I did 250 minus h, that would give me actually this distance, wouldn't it?
Oh,
That would be 250 minus h.
okay.
Now be careful. What's up? Still stuck.
The whole R thing is like totally confusing.
Okay, so once we get the, so your question is, once we get the equation, are we supposed to solve for h or r, right? So we're supposed to ultimately find the height of the water as a function of t. So I want to somehow take all this stuff, which I've got volume, right? I've got volume equals rate times time. I have the volume of a cone equal to 1/3 pi r squared h. And now I've got this similarity relationship between the full cone and the height of the water. I got to take all that stuff and somehow make it h out of t. Okay? So let's start with these volume equal rate times time, volume equal 1/3 pi r squared h. If I want to express height as a function of time, it would be nice to know a volume, a V number. And that's where this comes in. So if this right here is a rate of 40 cubic centimeters per a unit of second time, this is a volume, and this is a V. So I know what my V is. My volume is 40. Right? Yeah.
When you're solving for height, could you make the radius or whatever on the full size cone for the 250
Yeah.
50? Could you make, because 250 is equal to h, could you make the 50 1/5 h? So that would.
Yeah, but watch, you're going to actually get that answer right here. Watch what happens. You just actually did some of the work. So if we set this proportion up, we said the 250 is proportional to the h as the 50 is proportional to the r. So we get 250r is equal to 50h. And we want, okay, now here's the trick on this one. Do we want to solve for r or do we want to solve for h right now? What? Got some H people? Got some R people? What's our ultimate equation supposed to be in H in terms of a time? So I want to solve this for R so that I create R's into H's so that in my equation V equal 1/3 pi r squared h, that becomes an H now. And then over here for volume, I have a 40 thing going on. So we want to take this and we want to solve this for r. So if I did that, I'd have r is equal to what Jeff just said, 1/5 of the height. All right. Now we know what r is. And even starting to come together here. We go look at our volume, and we know that it's equal to 1/3 pi r squared h. And now we can replace r with 1/5 h. So now this is volume in terms of height right now. 1/3 pi times h over 5 squared times h. And we get pi world h cubed all over 75. 5 squared times 3. 5 times. Okay, where am I getting h cubed? H squared right there. Here, I'll do it step by step. get 1/3 pi times h squared over 25 times h.
Oh, what am I saying? Okay, never mind.
No, you weren't the only one. Don't worry about it. So we get pi h cubed over 75. Now that's again in terms of height. That's volume in terms of height. We're almost there. Now here's where the 40 cubic centimeter thing comes in. So we know that V is equal to RT. And, huh? Say that again.
1/5 each, because R is equal to H.
Well, yeah. But I was thinking more along the lines of that we've got 40. The RT is 40 times T. 40 cubic centimeters per second times time is our volume. Correct? But I don't need to worry about changing that R to an H. We're going to actually leave it that way, and that is because now I can come in and replace volume here with 40T and solve H in terms of time. So I solve this thing H in terms of time. We multiply by 75. That'd be 280 plus another 20, 300. Is that right? No. 3,000? 3,000 T multiplying by 75 is equal to pi h cubed. And then dividing by pi and then taking a cube root, I get height as a function of time is equal to 3,000 T over pi cube root. And there we go. So what was the trick on this one besides our similar? The trick was the volume equaling 40 cubic centimeters per second. That's a rate times a time, and that equals a V. So that's how we set V of H equal to 40T. We came up with V. Yes, sir.